Okay, so we're going to just practice finding solutions to matrix equations, systems of equations using matrices. These first few examples are all going to be the infinite and the many case because that's the hardest for students. Then I do think I threw in a couple of one variable case, one solution case, and no solution case. All right, these are all going to be the infinitely many. All right, so the first one, let me type it in. It's a smaller set, so it's going back to a 2 by 3. Right, first row is 3, negative 4, 6. Second row is negative 5 halves, 10 thirds, and negative 5. We do our RREF, row reduced echelon form. We get, alright, so you get this non-term at 0.1333333. And so you're actually going to have to, once you get that, RREF comes out. I don't know my calculator to pop up because I don't have it connected right now. I forgot this was the fraction case. So what you're going to do is you hit the math key on your TI-84, your math key, just like you would do a fraction if it was a decimal. You do the same thing. You're going to hit math, you're going to pick that fraction, and it'll put the entire matrix in fraction form. Alright, so pick math, the first one fractions, and then it'll put the matrix in fraction form. It will put it into the form 1, negative 4 thirds, 2, 0, 0, 0. So it'll convert that decimal into a fraction. So you hit math fraction on your calculator. Alright. It is the infinitely many case, right? 0 equals 0 is true, which means this is in a true equation. There's no false statements. There's no set x equals this, y equals this, and so the only default is, well, if there's no false statements, there's no specific x values and y value that equals, it has to be the infinitely many case. Alright, which means I have to set it up so I use this as my equation. So remember, xy equals my constant, and so my equation is x minus 4 thirds y equals 2. Because of the nature of the Gauss-Jordan, it's easier to put it in terms of y. So I'm going to let y be the arbitrary variable, which means I'm going to solve for x. All right, I'm going to get rid of the x, and it's really easy to solve for. The reason why it's easy to solve for x is because you already have the 1x. And so I just have to move the y term over. And so I get x equals 4 thirds y plus 2. There's my x value. And so my system is, my solution is the point where x has to be 4 thirds times y plus 2, and then y gets to be whatever I want it to be. Y is my arbitrary. I pick y and I have a solution, right? I plug it into this equation and I've got my x value. Right? And there is my arbitrary, my infinitely many case. Alright, next example, which is again going to be another infinitely many case. This one has 3 variables. It's got x, y, and a z. It's okay that those are zeros. Sometimes we want to find zeros. Right? In calculus, it's a major concept to be able to find something where you have a 0. Alright, so these just happen to be all my constants. In this case, are 0. So my first row is 1, 1, negative 5, 0. 2, negative 1, negative 1, 0. 4, 1, negative 11, 0. Alright, so it is a 3 by 4, so you have to make your matrix a little bigger. RREF, that matrix, it's going to come out 1, 0, negative 2, 0, 0, 1, negative 3, 0, 0, 0, 0, 0. Alright, so again, so my x, y, z equals constant. That just tells me 0 equals 0, which means these 2 rows I'm going to pull my solution out of. Right? It's an infinitely many case by default. So there's no false statement, so it's not a false one. There's no set x equals this, y equals this. This one you have to be careful because the zeros sometimes throw students off, but those are equal to my zeros, and that's fine. So it's x minus 2z equals 0, right? That first equation, x minus 2 times z equals 0, and then the second equation is y minus 3 times z equals 0, and so I do get those 2 equations out. Right, which again, due to the nature of the Gauss-Jordan, it always will get rid of the last thing. That's why when we do the y case, it's always the xy, when there's only 2, it's the y case, and when we do the xyz, it's the z case because of how we eliminate stuff. So the z gets eliminated. And so then z can be anything. the x and y that matters. And it makes sense because I can solve for x and I can solve for y if I know what z is. And so z is going to be the arbitrary variable. That means I need to solve for x and solve for y, which again isn't too hard to do. If I solve for x, I just have to add the z term to the other side. And so x equals positive 2z, and y the same thing. So y equals 3 times z. And so my solution is the point where x has to be 2 times my z variable, y has to be 3 times my z variable, and z gets to be whatever it wants to be. If I pick z between infinity and negative infinity, in order to find a point that's on my system, I just multiply my x by 2z, multiply my y by 3z, and z is whatever z is I picked. Right, so if I pick z to be 1, there's the solution 2, 3, 1. If I pick z to be 4, alright, then I get 2 times 4, which is 8, 3 times 4, which is 12, so I'd get 8, 12 for my y, and 4 for my z. Alright, and so this one again will give me any solution to my system. Alright, F. Two variable case again. Alright, so I'm going back to a 2 by 3, so my matrix A would be negative 5, 1, negative 3, 10, negative 2, 6, RREF. And this time I'm going to leave the decimals because you could hit the fraction key if you wanted to. But since these are, unlike the first example where it was 1.3333, it never ended, so I don't want to round. These are ending, the terminating decimals, and so you could find the fractions, and it's 1/5 and 4/5 if you wanted to. But you could also leave the decimals in this case because the decimals are perfectly fine answers too. Alright, so there's the 0 equals 0, which is true, and I left off a very important piece. This should have been 1, not 0. Should have been 1, negative 0.2, 0.6, then the zeros. And so again, this is where I'm going to get my solution. This just means it's true. So we get x minus 0.2y equals the constant 0.6. So y is the arbitrary variable because I can solve for x. When I solve for x, I just move that 0.2y to the other side, so x equals positive 0.2, right, because I add it to the other side. Plus 0.6, alright, so there's what x has to be. And so my solution is the point where x is 0.2 times y plus 0.6, and y is whatever the heck I want it to be. Alright, and that's the arbitrary case. I believe that's the last arbitrary case. I think G and H are both, one of them's a one solution case and one of them's a no solution case. Alright, so there's the arbitrary cases. Alright, G. So still a 2 by 3. My first row is 2, negative 8, 4. My second row is 1/3, negative 1/3. 4/3 is negative 2. REF. So plug it in my calculator, row reduce. And you should get 1, negative 4, 0 in the first row, 0, 0, 1. And as soon as you get this, that's saying 0 equals the constant 1. False. No solution. Which means H is my one variable case. Alright, so as soon as you see that, you're done. You don't have to go any further. No solution. Alright, next one. Oh, I have to do a little work before I can do the next one. This should have been H. So these two have to be reordered. I have to put them in standard form. So the first one's fine. 4x plus y equals 1 is okay. That one I've got to move my 2x over. So negative 2x plus y equals 4. And that one I've got to move my y over. So 3x minus y equals negative 4.5. And now I'm ready to go. And if you'll notice, there's no x term. Or sorry, there's no z term. There is an x term. There's a y term. And there's a constant term. And so this is more like the first example that I did when we introduced three equations to unknowns. There's no z, so don't put a z column in there. There isn't one. And so this is just going to be a 3 by 3. I'm going to have 4, 1, 1, negative 2, 1, 4. 3, negative 1, negative 4.5. RREF, row reduce. So I get, now I get that last row of zeros, but remember that last row of zeros just means there's no false statement, like the previous one. And so I go and look above and see what the equations tell me. Well, in this case, this is the x, this is the y, that's equal to my constant. And so my equation tells me there's one x, no y, and it equals the constant negative 1/2. The second line gives me the equation no x, there's one y, and it equals the constant 3. And so my statements are giving me one solution. The point negative 1/2, 3 is where all three of these equations meet, right? If I plugged in negative 1/2, 3, I would have a solution to all three equations. Alright, so just to kind of finish it up here, there's sometimes on the final exam, it's the final exam a lot of times, because of time, final exam's a long test, instead of making you type it all out on the calculator, what they'll do instead is they'll give you the matrix, and then you just have to read the solution. Alright, so there's a couple of examples of those cases. And so A is asking you, well, if that's your resulting matrix, what's your answer? Well, if you look at this last line, so if this is what your calculator gave you, your calculator was giving you 0 equals 1, and so you would choose no solution. If this is what so B would be a separate question. If this is what your calculator was giving you, well, that's that nice row diagonal of 1, so there's one x, there's one y, and there's one z, and it's equal to all of those constants. And so I get the one solution where x is negative 2, y is 3, z is 1, and so the solution is the order triple, negative 2, 3, 1 in that case. I didn't do an infinitely many case because we just practiced a whole bunch of them, but they'd ask you for an infinitely many case. Sometimes they'll give you the equation where it would look, like one of our infinitely many cases. They'd give you something like this, where they would just give you that as your matrix, and then you'd start from that and realize that that's your one solution, or no, infinitely many solution case. Alright, so just be aware they like to do that on the final exam because of time, right? So that you're not spending time just typing it in your calculator. You get into the real nitty-gritty, which is answering, what is the calculator telling me? Alright, so some final thoughts, just so that you know the difference between one solution, no solution, and infinitely many solutions. One solution cases are always, and we didn't do 4 sets, but you'd see how this would work if I had 4 sets, right? If I get that nice diagonal of 1, where I get 1x, and those hashtags mean numbers, so that would be my x equals my number, my y equals my number, and then this would be my x equals my number, my y equals my number, and my z equals my number. And again, we didn't do 4 cases, but I just add a variable like t. I'd have an x equals a number, a y equals a number, a z equals numbers, and a t equals a number. Alright, so whenever I get those nice diagonals of 1s, right, these are always the nice diagonals of 1s, and then my constants, and those are the only numbers involved, it's the one solution case. It's my one solution case. The no solution case on the calculator always results in the same. It doesn't matter what I have above. It's always the last row. And it doesn't matter how many zeros there are there, but it's always everything but the last number zeroes out. Right? I could have 4 if I wanted to. Everything over here zeroes out, but the last one is a 1. So it's 0, 0, 0, 0, 0, and then 1. 2 zeros and a 1. 3 zeros and a 1. That's always the no solution case, because that's saying 0 equals, not 0 equals 0, 0 equals 1. And so that's false. And so whenever you get the very last line, it's 0, 0, 0, 1, and it's always going to be 1 because of how the program works. So whenever it's 0 equals 1, false, no solution. Anything else is the infinitely many case. So if you don't get a false statement, you don't get your nice diagonals of 1s and your constants, by default, it's got to be the infinitely many case. Alright, and so what we're going to do is we're going to use this to solve systems. Now our systems, when we go solve them and do applications, will always be one solution cases. But you should be aware of all of the other outcomes are possible too. But we do try to keep our applications so they come out nice to the one solution case. And Okay, so that's the last section, is using systems to solve applications. And that's 3.3, which is the big section.